then you would just converge one iteration sooner. But say we choose x of 0 equal to 1 instead of 0.1. So we can plug this in now. X sub 1 is equal to 2 times 1 minus 12 times 1 squared, and we get negative 10. All right, so now we can plug negative 10 in. Negative 10. And then that gives me negative 1,220. So it really doesn't look like it's going to converge, but we can take it a step further. X sub 3 is equal to 2. And that gives negative. So now I think it's safe to say that there is no chance of this iteration converging. And that's the importance of choosing an initial guess that's at least close enough to the 0, to the root that we're looking for. So for this specific problem of computing a reciprocal, we can say that x sub 0 must be chosen such that x sub 0 is between 0 and 2 over a. This guarantees that the next iterate will at least be positive. And if we look at this graphically, you can see why it failed so miserably. Alright, so this is actually a graph, so we're computing the reciprocal of 12. This is a graph for the reciprocal of 8. But it has the same thing going on. Alright, so we've got that one there. And here. So let's first take a look if we choose x sub 0 equal to 0.1. So that's about right here. And then what happens, this is our tangent line. So this is x sub 0 right here. So here's our tangent line. It's actually already really close to the root. Now, this isn't just a sketch, but you can see how this iteration would definitely converge if we choose our x sub 0 as we did. Now, if I choose my x sub 0 equal to 1, so this is, we'll call this the old x sub 0, and this one the new. So here's my tangent line right here. And I end up on the other side of the x-axis where this is going to be negative. And so now you can see how that iteration got way off, because we would have a tangent line that would go way out here. And so that's why it's important to choose an initial guess that's sufficiently close to your actual root. So that's, are there any questions about that?
So why is it 2 over a in this case?
Why
since
the
it's
2 over a?
Since it is 1 over a, so it's
Right.
like 2 times the function, sort of.
Honestly, I'm not sure why. I'd have to look into it more. That's just the criteria that he gave for this specific
Right,
problem, just of computing the reciprocal. Now, in general, that doesn't apply.
Right.
In general, for a general function, it's just as vague as choosing something that's sufficiently close. And so you may have to have more information, or you may have to be given an initial guess, but it's kind of vague as to what the specific criteria is for choosing the initial guess in the general case. But it doesn't have to be extremely close, just sufficiently close so that something like that doesn't happen over there. So, yeah, so from this example you can see that we get a negative, and then the searching is just going to continue on in the wrong direction, on the wrong portion of the graph. So now what we want to do is analyze the convergence of Newton's method. So let's see, over here. Obviously we see that Newton's method converges faster than some of the methods y'all already learned, like bisection and fixed point iteration, but no numerical method is complete without its downfalls, and one of the downfalls is that we need to make sure that we choose the right initial guess first. So, analysis of convergence. So we're going to assume that f is twice differentiable. Assume that f is twice continuously differentiable. When the exact solution near the exact solution. So, can anybody think of why it would be important for f to be twice continuously differentiable? Because in the algorithm,
You're dealing with f prime.
right, exactly. We're dealing with f prime in the denominator, so we don't want f prime to be 0. As before, we can define error, or as y'all done for other methods, ek equal to xk minus x star to be the error after k iterations. So okay. So using the Taylor expansion around xk, wonder if I should move over for this slowly. So using the what we start with, I'll just come up over here.